Hello everyone, welcome to my channel Chemistry is Fun. Today we will study the topic shapes of some molecules, effect of unshared pair of electrons. In some molecules, as we will see, like in ammonia and water molecule, there are unshared pair of electrons, and how they affect the bond angle that we will see in this video today. Now ammonia NH3, in this nitrogen atom will be linked to 3 hydrogen atoms. So we have to see the bond angle of H and H. Now in this the electronic configuration of nitrogen is 1s2, 2s2, 2px1, 2py1, 2pz1. There are 3 p orbitals as we all know, and all the 3 p orbitals are half filled. All are having 1 electron each. So here we can see, or we can predict, we may think that in ammonia the 2p orbitals, these 2p orbitals can overlap with the 1s orbital of 3 hydrogen atoms, and we can get ammonia. But the experimental values which are obtained from ammonia for the bond angle H and H is found to be 107 degree. This is near to the normal tetrahedral angle. Okay, that is the ideal value of 109.5 degree. It is near to that, not exactly equal, but it is near. So we can predict that sp3 hybridization takes place here also. After sp3 hybridization, we will get 4 equivalent hybrid orbitals. So here 2s, 2px, 2py, 2pz, all these 4 orbitals will participate in the hybridization. After hybridization, 3 orbitals will have 1 electron each and one will be having 2 electrons. These half-fill orbitals, that is the orbitals after hybridization which are having single electron, that is they are half-filled, they form 3 sigma bonds with 3 hydrogen atoms, and one orbital which is having 2 electrons, that will stay back as lone pair. That will be a lone pair that is not participating in the bonding. So after that we find that ammonia has a pyramidal shape. In that nitrogen is at the apex. So this is the shape. See, this is ammonia. This is nitrogen atom. This is the lone pair, unshared pair, which does not participate in bonding. And there are 3 bonds with hydrogen. We can see first, second and third 3 hydrogen atoms. These are the bond pairs which are formed between the sp3 hybridized orbital of nitrogen and the s orbital of hydrogen. So there will be 3 bond pairs, and nitrogen is at the apex. Now out of the 4 pairs of electrons which are there in the sp3 bonding, one is sp3 non-bonding. You see this lone pair, it is not participating in bonding, so one is sp3 non-bonding, and other 3 are sp3 bonding, which are bonding with hydrogen. So there are 2 types of pairs of electrons. That is why the bond angle gets deviated from the ideal value of 109.5 degree. Because here you see, this is the lone pair, whereas this is the bond pair. The repulsion between lone pair and bond pair of electrons is always greater than the repulsion between bond pair and bond pair. So which is the bond pair? This pair of electron which is between nitrogen and hydrogen. You can see I am showing with a blue line now. This is the bond pair. All these are bond pairs between nitrogen and hydrogen. In case of bond pair of electrons, the electron is under the influence of 2 nucleus. Like in case of the bond pair of electron between nitrogen and hydrogen, it will be influenced by the nucleus of nitrogen as well as that of hydrogen. So its repulsive property is little less. Whereas in case of lone pair, it is under the influence of only 1 nucleus, so its repulsion is more. So this lone pair will repel the bond pairs and push them away. So the bond angle decreases from 109.5 degree and becomes 107 degree. I hope you all could understand. Because of this lone pair, unshared pair of electron, this bond angle decreases to 107 degree instead of being ideal value of 109.5 degree. Now we will further try to understand with another example of water molecule H2O. In that oxygen, we have to see the electronic configuration of oxygen. Oxygen electronic configuration is 1s2, 2s2, 2px2, 2py1, 2pz1. Now here the experimental value of HOH bond angle shows that it is 104.5 degrees. So this also suggests sp3 hybridization. This hybridization will be of the orbitals 2s2, that is 2s having 2 electrons. So which orbitals are participating? 2s2, 2px2, 2py1, 2pz1. So all these 4 orbitals will participate in sp3 hybridization, resulting in 4 sp3 hybrid orbitals. Out of these 4 sp3 hybrid orbitals, in 2 orbitals there will be 1 electron each, and these 2 orbitals can form sigma bonds with 2 hydrogen atoms. With 2 separate hydrogen atoms, they will form sigma bonds, that is single bonds. The other 2 orbitals which are having a pair of electrons each, they will be lone pair. The remaining 2 orbitals have 1 pair of electrons each, so they will not participate in any bonding. They will remain as lone pair. As you can see in this diagram, it is this figure, this is shown with orange color. These are the lone pairs, they are not participating in bonding. Here also we find that there is a deviation in the angle, that is due to non-equivalence of 4 hybrid orbitals. The 4 hybrid orbitals are non-equivalent because of the difference in the number of electrons which are present in them after hybridization. These 2 remain as lone pairs because they are having 1 pair of electron each. Other 2 orbitals which had single electrons, they formed bond with s orbital of hydrogen. So there are 2 bond pairs, and these 2 we can see they are the lone pairs. If we see the repulsion again, we find that the repulsion of lone pair is maximum, that is even greater than lone pair bond pair repulsion, and that is greater than bond pair repulsion. So these 2 lone pairs, they will repel maximum and they will push the OH-OH bonds as far as possible from them, because just now I told the lone pair electrons are under the influence of a single nucleus, so their repulsion power is more. So lone pair repulsion maximum greater than lone pair bond pair, that is even greater than bond pair electrons. That is why in case of water molecule, the bond angle is reduced to even much reduced from the ideal value of 109.5 degree. It is we get here nearly equal to 105 degree. That is, it's actually 104.5 degree. So it's a rounded up figure. So from here we can understand the effect of the lone pair, if it is present in a molecule, how it affects the shape, how we get a different bond angle than what is predicted due to hybridization. This deviation in bond angle in ammonia and water from the regular normal tetrahedral value, which we actually get in methane, it can be explained on the basis of valence shell electron pair repulsion theory, VSEPR theory, according to which for the maximum stability of a molecule, the valence electrons should be at a maximum distance from each other. They should be at a maximum distance of each other because of mutual repulsion. And deviation in the bond angle occurs due to different types of repulsions in a molecule. And as I just told you, the repulsions between all the electron pairs are not equal. The lone pair electron repulsion is more than lone pair bond pair electrons repulsion, which is greater than bond pair electrons repulsion. So we find different bond angles in different molecules. I hope you all could understand the topic which I discussed today. Thanks for watching my video. Please subscribe to my channel. Thank you all very much. Thanks. Please subscribe to the channel. Thank you.